1.3.1 Procedures as Arguments. Consider the following three procedures. The first computes the sum of the integers a through b. Define. We'll just put it in here too while we're at it. So, define the sum of integers. Define the procedure sum of integers that take inputs a and b. If a is greater than b, return 0. Otherwise, add a to the sum of integers applied to a plus 1 and b. The second computes the sum of the cubes in the integers in the given range. And so you do define the procedure sum of cubes that takes inputs a and b. If a is greater than b, return 0. Otherwise, add the cube of a and the result of sum of cubes of a plus 1 and b. The third computes the sum of a sequence of terms in the series, 1 over 1 times 3 plus 1 over 5 times 7 plus 1 over 9 times 11 plus etc., 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 which converges to pi over 8 very slowly. Define the procedure pi sum that takes inputs a and b. Oh, I forgot to put in sum of cubes, I think. Sorry. Sum of cubes. Okay. Define the procedure pi sum that takes inputs a and b. If a is greater than b, return 0. And I think that's actually the same over here. Oh yeah, and so then, otherwise add the result of dividing 1 and then the result of multiplying a times the result of adding a and 2. So all that. So add that first term to the second term of adding a and 4, and then applying pi sum to this, sum and b. These three procedures clearly share a common underlying pattern. They are for the most part identical, differing only in the name of the procedure, the function of a used to compute the term to be added, and the function that provides the next value of a. We could generate each of the procedures by filling the slots in the name template. So define the name with inputs a and b. If a is greater than b, return 0. Otherwise, add term of a to, and then the name, and then you have something to provide next to a, and then b. So then add those two together. The presence of such a common pattern is strong evidence that there is a useful abstraction waiting to be brought to the surface. Indeed, mathematicians long ago identified the abstraction of summation of a series and invented sigma notation. For example, sigma b n equals a, f of n is f of a plus up to f of b. To express this concept, the power of sigma notation is that it allows mathematicians to deal with the concept of summation itself, rather than only with particular sums. For example, to formulate general results about sums that are independent of a particular series being summed. Similarly, as program designers, we would like our language to be powerful enough so that we can write a procedure that expresses the concept of summation itself, rather than only procedures that compute particular sums. We do so readily in our procedural language by taking the common template shown above and transforming the slots into formal parameters. So we say, define the procedure sum that takes inputs term, a, next, and b, so 4 of them. If a is greater than b, return 0. Otherwise, add term a and term applied to a, and then the sum of term applied to the next of a and next b. So notice that sum takes as its arguments the lower and upper bounds a and b. Oh, so sum, term applied to next a, and then the next and b parameters. So all of those. So 3 things. Okay. Notice that sum takes as its arguments the lower and upper bounds a and b together with the procedures term and next. We can use sum just as we would any procedure. For example, we can use it along with the procedure I and c that increments its argument by 1 to define sum cubes. Define the procedure I and c that takes n as input to be n plus 1. Define sum cubes that takes inputs a and b to be sum cubes, to be the sum of a cube, to be the sum, and then cube procedure a increment to b. So cube a increment b. Okay, so sum, cube a increment b. Does that make sense? I think so. To do this, we can compute the sum of cubes for integers from 1 to 10. So sum of cubes 1 to 10. So let's do this. So what did we get? Some term we did. Let's do. So we have inc and sum cubes. Perfect. So now let's do this. Sum cubes 1 to 10. And we get 3025. With the aid of an identity procedure to compute the term, we can define some integers in terms of sum. Define the identity of x to be x. Define the sum integers of takes input a and b as sum applied to the identity of a increment b. Then we can add up the integers from 1 through 10. We can also define pi sum in the same way. Define pi sum of a and b, pi sum that takes a and b, and then define pi term that takes x. Pi term is you divide 1 times 1, and then you divide it by this, which is the multiplication of x and x plus 2. So then you do that, and then divide 1 divided by that. Then define pi next, which takes x, to be x plus 4. And then you sum the pi term applied to a and pi next applied to b. I think. Using the procedures, we can compute an approximation to pi. So the multiplication of a times pi sum, blah, 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 1 to 1000. Oh, I better put pi sum in there first. Okay. Okay, abort, please. Okay. There we go. Okay, cool. So now let's do this. Multiply h times the pi sum of 1 and 1000, and we get 3.1395, blah, blah, blah. Okay. Once we have sum, we can use it as a building block in formulating their concepts. For instance, the definite integral of a function f between the limits a and b can be approximated numerically by using the formula. The definite integral between a and b, f is equal to f of a plus the dx over 2 plus f of a plus dx over 2 plus f of a plus 2dx plus dx over 2, etc. up to dx. For small values of dx, we can express this directly as a procedure. Define the procedure integral that takes f, a, b, and dx as inputs. Define add dx that takes x as adding x and dx. Multiply the sum of f and then a plus dx divided by 2, and then add dx, apply add dx to b, and then multiply that whole thing by dx. So integral, so then we can do integral of cube of 1, 0, 1, and 0.1, 0.1. Okay, and then we get integral of cube, that one, of 0, 1, and 0.001. The exact value of the integral of cube between 0 and 1 is 1/4. So pretty darn close. 2.4999, so 2.5. Exercises, and we're good.